So, if you missed class when we went over 1.3, or if you want to just get a little bit more understanding, okay, let's take a look at this. So, we're dealing with solving equations. There's multiple ways you can deal with these, but there are rules that we need to follow. Okay, and these rules were developed, however we want to say it, by mathematicians. They went through and were able to solve in any circumstance that we can do stuff to equations and end up having them still work. Okay, so if we're looking at an equation, we usually have a few different parts. Okay, we've got usually variables, sometimes one, sometimes more, and sometimes we'll have numbers with them. Okay, so like 2x and 3y. The number in front is what we call the coefficient. And when they're squished with variables, it means that there's that many variables. So 2x is like x plus x. There's 2 x's there. We simplify it using multiplication. 3y, there's 3 y's being added together. But we simplify them with multiplication. Because remember, multiplication is simply repeated addition. It's a shortcut. So, we have those coefficients. We also have the variables. And the variables are the unknown quantities, right? We don't know what they are. We can figure out what they are if we think through problems, but we're basically solving to help us understand what they are. Okay, now we also have just other regular numbers, these constants, they're just numbers, part of it. Okay, we have operations like plus or multiply. Operations are simply the things that we do to the numbers, how they interact. Are they added? Are they subtracted? Are they multiplied? Which we should do the dot, not the times. We also see parentheses, or just a number and a variable means multiply. Or even, I suppose, on a computer you've got the little star asterisk symbol. Okay, you've also got divide, which we see often as a slash or a division bar, known as a fraction bar. Okay, so those are the main operations we're going to deal with. Okay, we also will later deal with exponents. Okay, so taking something to a power. Okay, now there's one other thing that's probably the most important part of an equation, and it has to do with the one that's probably the most overlooked, and that's the equal sign. And unfortunately, I think we've gotten into the habit as we teach math in making the equal sign seem like, well, that's the answer. So we'd look at this and say 2x plus 3y has an answer of 24, when that's really incorrect. Okay, and I know that probably the biggest thing that causes us to do that is calculators. A lot of calculators have an equal button, and when you type in stuff, so like 2 plus 3, you hit equals and it spits out your answer. Okay, and we've come to think of an equal sign as that's the answer, but that's not how it works with equations. Okay, and that's just not how the equal sign works. What the equal sign means is that both of these sides, the 2x plus 3y and the 24, are the same. They're equal. Both sides are the same. Now, they don't look the same. They're kind of like fraternal twins. Okay, they don't look the same, but they are the same. Okay, and that's critical to understand when we're solving equations, because that changes things. Now, this 24 just isn't an arbitrary answer. 24 is part of what's going to help us understand what x and y are. But let's simplify a bit. Let's take a look at these four equations. Okay, we've got 5 times x plus 3 equals 25. 5 times x plus 15 equals 25. 5 times x equals 10. X equals 2. Okay, and we look at them, we can see some similarities. They both have numbers, right? You've got a bunch of numbers here. You've got some operations going on. Except for this one, there's no operation, so I guess that's a difference, not a similarity. Okay. They all have equal sign. They all have variables. And if we really wanted to talk about it, if I put 2 in for each of these variables, my equation would work out, right? 2 would equal 2. 5 times 2 would equal 10. 5 times 2, 10, plus 15 would equal 25. 2 plus 3, 5, times 5 would equal 25. So they all have the x value of 2 as part of their result, I guess you would say. So yeah, there's some similarities. There's differences too. They have different numbers. They have different operations. Some are bigger, some are smaller. Okay, but they're all there. Okay, now, are these four equations the same? Okay, that's the question we're kind of thinking about. Are they the same? Well, we could argue, because x equals 2 in all of them, that yes, they are the same. Some of you may even be able to look at this and say, hey, there's kind of a step-by-step process going on here. But does that make them the same? Well, it depends on what you mean by the same. And in math, we actually have a better way of saying it. We call them equivalent equations. And equivalent equations are key to solving equations. Because the whole reason we solve an equation is to get it simplified to a point where we can say, this is what the variable is going to be in this situation, and then we use that. Okay, usually we have some sort of problem that we're tying this to, and so we would use that to then answer our question, saying, yes, we have 2 underwater pigeons. Okay, something like that. When we start with 1, we want to get it down, simplify it so much that there's no doubt what x is. Because if I gave you this equation, you know exactly what x is just by looking at it. And that's the power in solving equations. Okay, but we have to use equivalent equations, so a piece at a time, to get us down there. Okay, so let's talk about 3. How do we know which way to go, 3 and 4, and how do we know we can do that? So let's rewrite this. And I'm going to kind of draw a line here. Give myself some space. Okay. So, in math, they have a bunch of rules that say we can do certain things. Okay. We call them usually properties of inequality. Those are kind of the main ones we use with solving equations. Now, I don't like using those rules. I would rather have people be able to tell me why they're doing what they're doing and how it makes sense. That's more important to me. And once you understand that, putting the rules in place is really simple. Okay, so if we look at this and we say, how can we simplify this equation? We want to get this equation down to just x equals something, because that's the simplest form of that equation that we can come up with. Okay, well, whenever we see a 5 in front of here, in front of parentheses, not just 5 really, any number, it should key us into the fact that we are multiplying. In math, we have a term we call distribution. We're going to take this 5 and we're going to give it to each piece. So we give 5 to an x, we also give 5 to 3. And we multiply, because it's next to a parentheses, that means multiply. So I go 5 times x, which gives me 5x, because I can't simplify that further. Then 5 times 3, which I can simplify to 15. Now, notice we only changed the left side to get from here to here. Why is that? Okay, well, you've got to think about it like this. Okay, and this kind of maybe explains the whole thing. Let's imagine we've got 2 twins here. Okay, and these twins look exactly the same. Except one's a little sadder than the other. Okay, if I give this twin a cool hat and say they can wear it, they're different now, right? So I'd have to give this twin a hat. Okay, but I tell this twin not to wear it. Okay, are they still the same? Yeah, they're still a twin with a hat. Okay, that's kind of like this piece. Okay, they're still the same. Just one is wearing the hat, one isn't. Kind of, you could also compare it with this. The 5 times x plus 3 is equal to 5x plus 15. Okay, those are the 2 twins. One's wearing the hat, one isn't. Same idea, same concept. So all we did in going from this to this, okay, all we did is told that other twin, hey, dude, get your hat on. Okay? That's all we did. So did we change this left side? Or I guess did we change the right side? No. His hat just went from down here to up here. We didn't actually change him. Just, I suppose, his appearance. Okay, which isn't changing what's actually going on. So when you use that distributive property, okay, we used multiplication, or you could say the distributive property, distribution, to simplify the left side. Okay, but because we didn't change the left side, we don't have to change the right side. That's why 25 is 25. So we go to a more simplified equivalent equation. Okay, something that's more simple. Now, if I'm looking at this next piece, okay, if we're looking at this next piece, now I'm going to have to eliminate something. I'm going to have to change something because we want this x by itself. Because that's the whole point. We're creating equivalent equations till we get down to this guy. So in order to do that, I've got to get rid of the 5 and I've got to get rid of the 15. Well, which do we get rid of first? Well, when we're changing something, we want to get rid of what's simpler. Now, I could try to divide by 5 to separate those. The problem is I'd have to divide everything by 5, which I could do in this case. Okay, but that's not going to get us to our next equivalent equation. Which, side note, you can do this. Okay, if this makes sense to you, do it this way, and you can create different equivalent equations to get you to your end result. But for us, we're going to say, okay, we've got this plus 15. How are we going to get rid of a positive 15? Well, we're going to have to eliminate it by subtraction. Okay, so that would eliminate and become 5x plus 0, which 5x plus 0 does nothing, so we get rid of it. There's actually a rule in math that is called the additive identity property of 0 that says adding 0 does nothing, so we can just eliminate it. But now, see, we've gone from this just to the 5x, which that is different. Okay, we did change something. So we have got to do it to the opposite side. Take our twin example again. Okay, let's say we take one of our twins and we lop off their leg. Okay, they are no longer twins. And he'd probably be bleeding. He'd probably actually fall over, so we better prop him up with a cane or something. Okay, now we've changed something on one twin. So now they're no longer twins. Oh no, but we don't want to lose their twinniness. Okay, we want them to stay twins. So what do we have to do? We have to lop off the leg on the other one. Okay, same idea with equations. I subtracted that 15 and changed the left side, so I've got to subtract 15 and change the right side. I've got to maintain that equality in my change. So we subtracted 15 to change the left side and eliminate the 15. But to maintain equality, and I'll just put an equal sign, we did the same to the right. Okay, and that's important that we take that into account. So now this last step, we've got 5x equals 10. Okay, we changed both sides, but we did it in a way that we maintain their equality. So we can do the same thing. To separate 5 from x, it's 5 times x, so I do the opposite. I divide by 5. But once again, back to the twins. Okay, now we just eliminated another piece of them. So I did it to one side, so now we've got to do it to the other side. Okay, and let's put some band-aids here. Keep them from bleeding, huh? But do you see that with equations, just like with twins, to maintain that equality, probably should clean this up before anybody sees. There we go. To maintain that equality, that's what we're doing. We've got to do it to both sides. So we divided, I'm going to just kind of write this over, divided by 5 to change the left side and eliminate the 5 times. But to maintain, we had to do it to both sides. So now that becomes 1x, which 1 times x is just x. 10 divided by 5 is 2. Now we've brought it down to our simplest form of an equivalent equation, something that we like. So, how do we know we can do that? Because of that equal sign. That equal sign says it doesn't matter what we do to both sides, as long as we do it to both. Okay? As long as we do it to both. Now that I've, used that, let me give these twins a little super awesome magic elixir of regrowth. Because, I would hate to leave these twins without any sort of body parts. And now they're both happy-ish. Or they have tusks and fangs. One of the two. Anyway, so that's how we deal with it. So let's take a look at one example here. Okay? Now, there was a lot of examples, but I wanted to keep this one shorter, and I do a lot of equations on the homework of 1.3. So this is just kind of one example to show what I expect when we're doing these. So I look at this. We've got a lot going on in this equation, don't we? But the first thing I should notice is I've got some parentheses and some numbers in front. So I need to simplify those. We need to simplify using distribution. And because I'm simplifying, remember, like we said, we're not changing this. 7 times 7 minus x is the same as 7 times 7 is 49, minus 7 times x, 7x. They're the same. I didn't change that, I just simplified it to an easier number to do. I didn't get rid of any numbers. I just took this 7, times it by this 7, and by that x. 49, right, is really 7 times 7. So I didn't eliminate a number, I just kind of put them together. Okay, kind of like when you bake a cake, or any sort of food. You don't eliminate the ingredients by putting them together. You just put it in a different format that is much more enjoyable. Okay, so negative 4 times negative 3 is negative 12x. Negative 4 times 7 is negative 28 minus 8x equals 49 minus 7x. So we didn't actually do anything, so I didn't have to multiply the 7 or the negative 4 by both sides. Now here's one more thing that we can do to simplify. Negative 12x minus 8x. Okay, these are still x's. Okay, they're just a bunch of x's being added together. Negative 12 of them and negative 8 of them. Okay, so I'm combining them just like if I had negative 12 minus 8. I don't go around walk around saying negative 12 minus 8, negative 12 minus 8. I say negative 20. Okay, we're just combining them. Once again, we're simplifying by combining like terms, but we are not eliminating them. Okay, so negative 12x minus 8x, negative 20x minus 28 equals 49 minus 7x. What did we do? We still simplified by combining terms. Okay, the x terms. Alright, so now what's the next thing we can do? Now we can start saying, okay, I've simplified these as far as I can. A variable term and a regular number, I can never combine those. So now we've got to look at figuring out what we can do with our numbers. So I'd look at this and say, hey, I can add 7x to both sides. So because I'm now changing this, I'm getting rid of that negative 7x by adding 7x to it. Because I'm changing that right side, we have to change the left side by adding that 7x. To maintain our equality, we've got to do it to both sides. So negative 20 plus 7 is negative 13x. Why can we do that? Well, we added 7x to both sides, okay, using the addition property of equality to be technical. But we added 7x to eliminate the negative 7x. But we did it to both sides to maintain the equality. maintain equality. So now we want to combine the numbers, because I can't simplify this left side. So how are we going to get rid of that negative 28? We're going to add 28 to both sides. Okay, so we're adding 28 to both sides to, once again, eliminate negative 28 from the left, but we do it to both to maintain equality. So that becomes 0, which we eliminate because adding 0 does nothing. And then we add these. And we get negative 13x equals 77. So now this last step, we want to separate this negative 13. So we do the opposite. It's multiply, we divide. We end up with x equals, because negative 13 over 13 gives us x, equals this number, which is, so this 77 over 13, negative 77 over 13, I think it's like 5.9 or something. That doesn't really matter. The point is that we've brought this very weird looking equation, very complex equation, using all these other sets of equivalent equations, and we've brought it down to this one that we look at and we know exactly what's going on. We know exactly what x is. By the way, we divided by negative 13 to eliminate the 13, did it to both sides to maintain equality. Okay? In the math world, they call that the division property of equality. Okay? And that's all we do when we're solving. We're always trying to get down to that simplest form of the equivalent equation.